Hello students and welcome to the physics classes. Today we are going to study a very important chapter of physics and it is very important from your NEET and mains perspective also, right? This particular chapter, I'm not going to tell you the name. I will give you a hint. I will ask you certain questions and I want you to answer which chapter we are going to study today. Okay, so without any much ado, let's get started. Okay, now you can see my, wait, let me share you my screen. Yes, I hope you can see the screen now. Now, tell me what will happen to an object if I remove it from a stable equilibrium. Okay, I hope that you will not be aware with the term this stable equilibrium. Equilibrium was okay. We studied in forces chapter. What is this stable equilibrium? Okay, no issues. Let me pose you a simple one. You'll be able to answer that one. Now, what will happen to a pendulum's bob if I take it at an extreme position and leave it? Yes, very good. It will oscillate. So now can you tell which chapter we are going to study? Yes, very good. That is oscillations. So in this particular chapter, let me tell you what is the limit of this chapter, where we are limiting ourselves. Okay, so in this particular chapter, we are not considering large oscillations, rather we are considering only small oscillations. So what are small oscillations? Small means large oscillations. Why we are not considering? If we consider large oscillations like this. Okay, so in that particular case, what will happen? The circular motion of the bob will also come into role, right? And there the centrifugal force, centripetal forces will be there. So the problems will become more complex. So firstly, we will deal with small oscillations and then gradually we will see the large oscillations and damping forces also. Okay, and then firstly, let us restrict ourselves to the small oscillations. Now, on the basis of repetition, there are four kinds of motion. Okay, so like initially I have told you in the previous classes that there are several kinds of motion like translational, rotational, vibrational. Okay, but I am telling you on the basis of repetition, there are four kinds of motion. Okay, the first one is your periodic motion. What are periodic motion? Any motion, any motion that repeats itself after certain interval of time is called periodic motion, right? Like the fan that is rotating above my head or your head is periodic motion because the fan blades are rotating and they are repeating their motion after certain interval of time. Okay, what are non-periodic motions? All the motions which are not repeating themselves, like an ant crawling somewhere, right? And if I'm writing something on a paper, on a piece of paper, so all these motions are not periodic because they are not repeating themselves after certain interval of time, right? But now the periodic motion also is divided or distributed in two kinds. Okay, the first kind is the periodic motion which are not simple harmonic. Okay, and there are few motions which are periodic and simple harmonic. Okay, now what are periodic but not simple harmonic motions? The finest example will be your rotation of all the planet around sun, the fan blade which is rotating. So all these are periodic motion but are not simple harmonic, right? Now if I am skipping a rope, okay, so all these are not simple harmonic motion. Okay, now what are simple harmonic motion? So all the motions which can be expressed in terms of sine and cos, sine and cos, sin x plus cos x. So all those functions which can be represented in terms of sine and cos, they are said to be periodic and simple harmonic motion. Okay, so all the functions which are represented in terms of sine and cos are called simple harmonic motions, and all the simple harmonic motions are periodic motions also. Okay, but all periodic motions are not simple harmonic, like the motion of fan. Now, the first slide which I shown you, okay, the first question which I asked, what will happen to an object if I remove it from stable equilibrium? Okay, so now I'm going to tell you what is this stable equilibrium. Okay, now see this dy by dx is 0. Okay, forget the mathematics. Let me give you a simpler example. Okay, now if I wait, let me do it here. Now, if I take a bowl, okay, or bowl, whatever you say, and I put a marble over here, there is a marble over here. Okay, now if I displace this object from here to here and leave it, what will happen? Yes, it will come back and it will continue to oscillate like this, right? Now take another example. Let me change ink. If I place that same marble on a hill, okay, I have placed that same marble on a hill. Now what will happen if I displace the marble? If I displace it like this, is it going to come back again? No. So this particular condition is your unstable equilibrium. So let me take this one. So this is your stable equilibrium. I'll write here. This is your stable equilibrium condition, and this is your unstable equilibrium condition. Okay. This is your stable equilibrium where the object is coming back to its position by its own. So that is your stable equilibrium. What is unstable equilibrium? When the object is not coming back to its original position by its own. Okay. So these curves which I have made are nothing but a potential energy versus displacement curve. Okay. Now a potential energy versus displacement curve. So this is your X and this is your potential energy. Okay, U. This is your potential energy, and this also is your potential energy versus displacement curve. Now, in forces chapter, I had told you that for a conservative field, F is given as force is what? F is equal to minus du by dx, right? Force is minus du by dx. So in equilibrium, what is equilibrium? When many forces are acting on a body, but all of them are cancelling each other. So that particular condition is known as equilibrium condition, when the net force on the body becomes zero. So net force is becoming zero, right? Net force is zero. So there must be du by dx must be zero. Therefore, dy by dx is zero. See here. For both the equilibrium conditions, be it stable or unstable, the potential energy, the slope of potential energy versus displacement curve must be zero. Du by dx must be zero. See these points, the maximum points at here and here. The slope is zero, right? So therefore, dy by dx is zero. This is your equilibrium condition. Many times questions are asked like this. Okay, so like they will give you a function and they will tell you that at that particular point or at what particular point the equilibrium condition will be there. Okay. Next, d2y by dx2 must be positive for stable equilibrium and d2y by dx2 must be negative for unstable equilibrium. How? In your mathematics, you have studied maxima and minima, right? So what is maxima condition? That the double differentiation must be negative, right? The maxima condition is double differentiation must be negative. So that is C, your maxima point, and double differentiation must be positive for minima point. See here, the object is at minimum position in this particular case, and in this case, the object is at maximum position. Okay, so I hope you have understood this concept. Now these are properties of SHM. Okay, I want you to pause the video and look at all those properties and note it down somewhere. Okay, because if you don't make notes, I can guarantee that you are not going to get anything. You will forget all the things. Okay, now firstly, I'll explain you all these points, don't worry. So firstly, as I told you that in this particular chapter, we are considering only small oscillations. So SHM are small oscillations only. Okay, next is acceleration is in opposite direction of displacement. Now see, if I make a spring mass system, Okay, suppose this is a spring and this is a block of mass m. So pardon me for my drawing. Okay, so this is a block of mass m. If I stretch it up to this point, so what will happen? The spring will try to restore itself, right? And if I compress the spring, what will happen? The spring will try to expand itself. So here you can see that the force that the spring is offering to the mass is always in opposite direction of the displacement, right? So therefore acceleration is in always opposite direction of displacement. Now velocity is maximum at mean position and zero at extreme position. Okay, now see, take an example of your pendulum. This is a pendulum. Now if it is oscillating, okay, if it is oscillating like this, so what will happen? At extreme position, the bob is stopping and coming back, right? Similarly here also the bob is stopping at this point and coming back. So where the bob is stopping? At the extreme positions. At the extreme position the bob is stopping. So therefore at extreme position the velocity is zero, but at mean position at this particular point, the velocity will be maximum. Okay, now acceleration is maximum at extreme position. It is reverse of velocity. Acceleration is maximum at extreme position. Let me rub that. Okay, now acceleration is maximum at extreme position. Why? Because see, I told you that acceleration is in opposite direction of displacement. Okay, so where the displacement will be maximum, the acceleration will be maximum. At this particular point, displacements are maximum. Okay, at extreme points, displacement are maximum. So therefore, acceleration will also be maximum at this particular point, the extreme position. The acceleration will be maximum and zero at mean position, because then there is zero displacement. So zero displacement, that means zero acceleration. Okay. Now, kinetic energy. Wait for a while. Now, kinetic energy is maximum at mean position and zero at extreme position. Okay. Now, kinetic energy is maximum at mean position. How? Velocity is maximum at mean position. So, kinetic energy will also be maximum at mean position. And if velocity is zero at extreme position, that means kinetic energy will also be zero at extreme positions. Coming to potential energy. Now, see here, if you consider these levels, oh, sorry. If you consider these levels, okay, take a pen. Now see, this is your mean position, right? And this is extreme position. This is extreme position. So you can see that mean position, the object is at lower level, and at extreme position, the object is a bit higher level. So therefore, in mean position, the potential energy is minimum, whereas at extreme position, potential energy is maximum. Simple. Let's proceed ahead. Now, this is a simple derivation of SHM. This is very important from your board perspective, but sometimes they take some certain takeaways from this particular section. Like they can ask the value of phi, they can ask the value of amplitude, they will give you two phase functions. Okay, and they can ask a question in mains and NEET also. Okay, now let's proceed with this derivation. Like in the previous slide, I told you that acceleration is in opposite direction of displacement. Okay, opposite direction of displacement. So that is what I have written here mathematically. Acceleration is in opposite direction of displacement. Acceleration is proportional to negative of displacement. Acceleration can be written as d2x by dt2. Right. Now see here, we are differentiating this x and we are getting minus x. Right. So what function should we take that we differentiate it twice so we get negative of it? So such functions are your sine function and cos functions. So therefore, I have taken both the solutions. X is equal, let x is equal to sine also, and x is equal to cos also. Okay. How you will understand this physically? See, if I draw sine curve, it is like this. This is your sine curve. Okay. And if I have to draw cos curve, so this is your cos curve lagging by pi by 2 phase difference. Okay. So this is your cos curve. Now, how will you understand this physically? If I am taking a pendulum, okay, if I am striking it here and it is oscillating like this, okay, it starts oscillating like this. So this particular pendulum is following this motion, the sine motion, because it is starting from mean position. Okay, and if I take the pendulum at extreme position and leave it without striking or anything, I just leave it, so it will oscillate like this. Again, it will come to this position. So the pendulum is starting its motion from one of the extreme positions. So that becomes your cos curve, right? So therefore, we have taken both the solutions, sine as well as cos. Okay. Now x is equal to x1 plus x2, because we are taking both the combination x1 and x2. Let C, this C and D, this C and D, I'm assuming them to be a cos phi and a sin phi. C is equal to a cos phi and a sin phi. So a will be what? Under root c square plus d square. Just square and add both of these. Square and add both of these, you will get a. Okay. Now, if I substitute this value over here in these equations, okay, in these equations, this equation particularly, okay, so what will I get? X is equal to a cos phi sin omega t and a sin phi cos omega t. A can be taken common, right? A can be taken common, and x becomes your, see, what will we remain with? Cos phi sin omega t and sin phi cos omega t. So what is sin a cos b plus cos a sin b? Yes, that is sin a plus b. So x is equal to a sin omega t plus phi. This is your general equation of SHM. This is your general equation of SHM. If I differentiate it, if I differentiate x, so what will I get? X dot. If I differentiate displacement, what will I get? Velocity. And if I differentiate velocity, what will I get? Acceleration. Right? Now see here, here also we are having sin omega t plus phi. In displacement also we are having a sin omega t plus phi. Right? So here you can see that acceleration, like where we started, acceleration is proportional to negative of x. That is what we are getting also here. Right? Chalo. What are major takeaways from SHM equation, the standard equation? Now x is your a sin omega t plus phi. X is what? Displacement. This is your instantaneous displacement. X is instantaneous displacement. A is your amplitude. What is amplitude? The maximum displacement from mean position of an object is called your amplitude. The maximum displacement from mean position, that is your amplitude. What is omega? Angular frequency. Now see, if the bob is oscillating like this, okay, so this particular displacement, this displacement from mean position to the extreme position, this is your amplitude. Okay, if the angle we are considering, at each instant the bob is changing its angle, right? The bob is changing its angle from the point of suspension. If we see, so the angle is continuously changing, right? So this, the rate of change of angle, this is your angular frequency, 2 pi by, and how is time period related with your angular frequency? That is 2 pi by omega. What is time period? The time taken by the bob to complete its one oscillation, to complete one complete oscillation, to execute one complete oscillation, how much time the bob is taking, that is called as your time period. Okay. Now next is your frequency. What is frequency? It is inverse of time period, or the number of vibration in a unit time. That is called your frequency. I'm not going to tell you the SI unit of frequency, that you have to tell me, because you have studied this in class 9th also. Okay. The SI unit of frequency, comment down in the comment section. Okay. Now this phi is your phase constant. It will tell you that in which direction or at which position the particle which is executing SHM, it is at what point it is. Okay. Next. Now here I have told you the velocity of the particle, right? If I have the velocity of the particle, can't I derive the kinetic energy? Yes, of course I can. So that is your kinetic energy equation. See here, mv square. Okay, I have substituted the value of v, so I got this. Similarly, in forces chapter, I have told you the energy stored in spring, that is half kx square. So in place of x, I have substituted this. Now I have got this sine function, I have got this cos function, rest all are same. So I have added this and I have got m omega square a square. Done. Okay, now after this, only few things are remaining in this chapter, that is your uh, resonance and your what do we say, that damping. Okay, the resonance and damping is only remaining and rest everything is done. Okay, now let's revise what have we done till here. So we considered oscillations, that small oscillation. We saw the types of motion, periodic, non-periodic, what are periodic motions, that what are SHM that can be considered in terms of sine and cos, what are periodic but not SHM, right? We saw the condition of equilibrium, we saw the condition of the stable and unstable equilibrium, right? We saw the relation between force and potential energy also. Then we discussed the properties of SHM. We saw the derivation of SHM. Here we calculated the amplitude also, we calculated phase constant, we calculated instantaneous displacement, standard equation of SHM, velocity of particle and acceleration that is being forced on the particle. Then we saw the major takeaways from the SHM equation and then we derived the energy. Now these practice questions I am giving you for your assignment that you have to practice and come tomorrow in the next class. Simple questions I have given, don't worry. The first one is your, which of the following functions of time represent motion of particle in SHM? Sorry. So this is your sine omega t cos omega t. One cos function is there, sine cube t, 1 plus. Now this type of question, I told you in the very first slide that all the motions which are linear combination of sine and cos, they will be your SHM equation. So see in which of these there are linear combination of sine and cos and you will get the answer. Simple question. Similarly, this also, yes, displacement of particle is given, x is equal to a sine square omega t. Can you convert it in terms of sine and cos? If you can, so then you calculate the frequency. Okay, which one will be your the correct answer, omega by pi, or is it non-SHM also? Okay, so that you have to tell. All these are repeated questions. Here that SHM versus kinetic, SHM versus potential energy graph is plotted and you have to choose the correct potential energy curve. This question is asked from this point. See here, potential energy is minimum at mean position, maximum at extreme position. So maximum at extreme position. So tell in these graphs which one is your minimum at mean position and maximum at extreme position. Okay, so see the correct and choose the correct option. This one here is your two functions are given, y1 and y2. Okay, you have to square and add these and tell that what will be the value of displacement. Okay, so amplitude, what will be given? Amplitude. So that you have to solve. Okay, and if you're not able to solve any of the question, you can comment it down and I will tell you the solution in the next class. Thank you. Have a nice day. See you in the next class. Bye-bye.